Okay, here we go with section 10.7. This is about some reactions of acids and bases. And well, they start off, the slides start off with an example of gastric acid being produced in the stomach. And there's, the point is that acid-base chemistry is very important in biochemistry. And this section, we're going to learn to write balanced equations for reactions of acids with metals, carbonates, bicarbonates, and bases, and also to calculate the molarity or volume of an acid from titration information. So we got quite a few things to do, so let's get started. Acids undergo a number of reactions, and some of these are the following. They can react with metals, and just the metals, sodium, zinc, iron, to produce a salt and hydrogen gas. The salt is an ionic compound that's derived from the anion of the acid, and the cation, the positive ion, is going to be coming from the metal. They can react with bases to produce a salt and water, and they can react with bicarbonate or carbonate ions to produce carbon dioxide gas. They define here a salt as an ionic compound that does not have hydrogen as the cation or hydroxide as the anion. So salts would include sodium chloride, which you know is table salt, and potassium chloride and so forth, and the halides, and then sodium carbonate could be seen as a salt. It depends on the reaction. This is an example of one of the reactions between, two of the reactions actually, between metals and acids. The acid is hydrochloric acid here, and you see what's going on. In the first one, potassium reacts to give you hydrogen gas, and the salt is potassium chloride. In the second one, the zinc reacts to give zinc chloride plus hydrogen gas. So what's going on is you already know that metals like to form positive ions. So metals are going to give up one or more electrons so that they can get that, that noble gas configuration. And something, of course, has to pick that up. Something, of course, has to get those electrons, and that's going to be something with a positive charge, and the only thing with a positive charge in this is going to be the hydrogen ion, so H+. So you're going to get hydrogen taking on an electron from potassium. Two hydrogen atoms are going to form hydrogen, the diatomic hydrogen, and you get hydrogen gas. And the similar thing happens with zinc. So writing balanced equations, there's going to be a procedure for that, and we're talking about here magnesium metal with HCl, hydrochloric acid, and aluminum metal with nitric acid. These are the reactions, and the procedure goes like this. You write what we're asked to do is they want to write the balanced equations for these. All right, you see this is already balanced. Looks like it. So let's go ahead and balance this. They were telling us to balance the reaction where there's not a slide actually doing this. You're starting out with magnesium reacting with hydrochloric acid, and I don't have these labels here for solid and aqueous and gas and so forth. We'll put that in later. We need to balance this. Then let's just see what we need to do. Let's start with the hydrogen. We see here that we're going to need two hydrogens we're going to need two HCl's to get two hydrogen atoms to give you the diatomic hydrogen here. So let's just put this 2 in here. And now we've got, what do we have here? We have magnesium. We got one magnesium, two hydrogens, two chlorides, two chlorides. It looks like we're balanced already, so that was pretty simple. So we have magnesium, which is going to be a solid, plus two HCl's, which is going to be aqueous, and magnesium chloride, which is going to be aqueous, and hydrogen, which is going to be a gas. All right, so there's your reaction. But it's actually pretty simple in this case. Some of these aren't necessarily all that simple. Aluminum metal with nitric acid, let's take a look at that without the coefficients, just for some practice at balancing. It's probably a good thing to do. We have aluminum plus nitric acid, HNO3, and that's going to give us aluminum nitrate. And what's aluminum nitrate going to look like? Okay, well, nitrate itself is a -1. Aluminum is +3, so it's going to be, you're going to end up with this. See how that's going to work. And there's going to be hydrogen gas. And now we've got some things to do here. To start off, we're going to need at least, the way this is written, we're going to need at least 2 hydrogens here, and we're going to need at least 3 nitrates. So let's go ahead and let's go ahead and put the 2 hydrogens in here. Let's balance these hydrogens. You see, we have the, okay, so now we're balanced with 2 hydrogens to give you 1 molecule of hydrogen gas. And now we've really got a mess because we got 2 nitrates here and 3 here, which means that we're going to have 6 of something. So let's multiply. Let's balance get these nitrates balanced. Let's multiply here by, let's do it like this. We have aluminum plus 6 HNO3 goes to, and it's going to be, we're going to have 2 aluminums. And now we have to balance these hydrogens again. Remember, we had 2 here. Now we have 6 hydrogens, but that's easy. We just have 3 H2. And all we have left to balance is the aluminum. So that should be, we've got 2 aluminums, 6 hydrogens there, 3 times 2 is 6 hydrogens there. We have 6 nitrates, and 2 times 3 is 6 nitrates. It looks like we're good. It looks like we're balanced. So, sometimes you're going to need to balance these reactions. And you see 2, 6, 2, and 3, and that's the way the thing works. Acids also react with carbonates and hydrogen carbonates, or bicarbonates, to produce carbon dioxide gas and a salt and water. And if you think about the Lowry-Bronsted definition of acids and bases, you should be able to see that in the Lowry-Bronsted or Bronsted-Lowry sense, carbonate is acting as a base. It's going to pick up two hydrogen atoms, or 2 hydrogen ions, to give you carbonic acid. That then breaks down to give calcium to carbon dioxide and water, and then you're left with the salt calcium chloride. And bicarbonate acts the same way, except it only needs 1 equivalent of hydrogen ion in order to get to carbonic acid. This is a stepwise reaction, and I did put together a little bit of a slide just to show you what's happening. This is going in steps. You see the 2 HCl's react with calcium carbonate. You first form carbonic acid and calcium chloride, but the carbonic acid itself is unstable, so it loses carbon dioxide to give you the gas and water. And the same thing happens with sodium bicarbonate. This is something that the book doesn't mention, but I thought I might mention it it might make it a little easier to understand if you realize there's two steps going on in this reaction. Anyway, we have here, let's write balanced equations for the following reactions. Okay, well, this one, at least now, this is not a balanced reaction yet, or it doesn't look like it. So let's balance this reaction. So magnesium carbonate and hydrobromic acid. So let's clear this. Magnesium carbonate plus HBr. And so what do we know? Well, this is a reaction with a carbonate, so we know that we're going to get carbon dioxide off. We know that we're going to have, well, there's a magnesium is going to stay magnesium ion, and this CO3 is going to be gone. It's going to be as CO2 as carbon dioxide gas. That carbon's going to be gone. So the negative ion is going to have to be bromide. So it's going to be MgBr2, because remember, magnesium's a +2 or 2+, and we're going to have water. Let's balance this. We have magnesium. Well, we have a couple options here. We have we can balance the bromide here. You see bromine. There's two bromines here, and one on this side. So if we double this, we have magnesium bromides. Okay, and now look, we've balanced the hydrogens on the water. And the carbon dioxide will one carbon here, 3 oxygens, 2 and 3 oxygens. So it looks like we're done. Let's look at this one more time, just to make sure. Magnesium, 1 carbon, 3 oxygens, 2, 3 oxygens, and 2 hydrogens, 2 bromines. So we're done with that. And take a look at the other one. We can. This other one looks like this one's going to be a little easier. The the hydrochloric acid and sodium bicarbonate is going to be a bit easier. So we'll just go ahead to the answers they give. You see, you really don't have to do anything as far as coefficients with the second reaction, but these are the reactions. So the carbonate is going to end up giving you 1 water. Each carbonate is going to decompose to give you a water molecule and a carbon dioxide molecule. And that's going to be true of this type of reaction. Then we have neutralization reactions, which is a typical acid-base reaction. We're going to be talking about titrations in a little bit, and this is what's going on in a titration. In fact, I believe the example of a titration that they're going to use is going to be hydrochloric acid and sodium hydroxide. So you have an acid-base reaction. In an acid-base reaction, you're always going to get a salt and water. So hydrochloric acid is going to react with sodium hydroxide, and you see what's going on here. Let's take a look at this. In fact, no, actually, they actually have a slide here on it. So you see what's going on is, let's back up again. You realize, you know now that hydrochloric acid is totally ionized in water, so there's hydrogen ions and chloride ions, and sodium hydroxide is also ionized with sodium ions and hydroxide ions. So you have a rather complicated collection of things there, and this equation looks pretty busy, but I put the acid and base parts in red so you could pick those out. See, what's going on is the hydrogen, you have 1 hydrogen ion, 1 hydroxide ion react to form water, and that leaves you sodium ions and chloride ions, which are, you could call these spectator ions. So the overall reaction, the net ionic reaction, we would call it, is just a hydrogen ion and hydroxide ion going to water. What's left is the salt, in this case sodium chloride. Now, balancing neutralization reactions, a little bit of a procedure there. As usual, you write the reactants and products, and you have the salt there. And the first thing you do is you balance the hydrogen ion with the hydroxide ion in the base. And that's going to be fairly simple because you have you have to have an equal number of hydrogen ions to a number of hydrogen ions equal to the number of hydroxide ions. So you look at the way this is set up right now. Well, what they do is, you see there's 2 hydroxides, so you're going to have at least 2 waters, which means 2 hydroxides, which means you're going to need 2 hydrogen ions. So there's going to have to be 2 nitric acids in order to balance that. And when you do that, you put the 2 nitric acids in there, you see that everything works out nice. Now you have 2 water molecules, and now you have a salt. Now you have to figure the salt out. Well, the salt's going to be, this is nitric acid, so the salt's going to be a nitrate. And you just write it from the remaining ions. So you have 2 magnesium hydroxide molecule, 2 nitric acid molecules is going to give you 2 water molecules, and then what's left is magnesium nitrate. So let's take a look at some of these things. We can do the whiteboard with this. We look at, let's go to the HCl plus aluminum hydroxide first. And then you notice number 2 is going to look awful, but it works out. You have hydrochloric acid, aluminum hydroxide is going to go to aluminum chloride and water. So we have hydrochloric acid. Let me clear this here. Okay. You have aluminum hydroxide plus hydrochloric acid. It was a hydrochloric acid, wasn't it? Yes, and I wrote these in the wrong. I wrote these in the opposite direction. So let me correct that. Let me do this. No, undo that. Here. Getting practice working with this whiteboard thing. Okay, this is the way the text is doing it. And that's going to give you aluminum chloride and water. Remember, this is an acid-base reaction. First thing you do is you balance the hydrogen and hydroxides. So here you have 3 hydroxides. Here you have 1 hydrogen ion. So you're going to need 3 hydrochloric acids at least. And that is going to, what's that going to give you? Okay, that's going to give you 3 water molecules. So that's set. All right, so you have 3 hydrogen, 3, so you have a total of 6 hydrogen atoms, right? 3 from hydrochloric acid, 3 from hydroxide. It's going to give you 3 waters. Okay, right now aluminum looks like it's okay, and chloride looks like it's okay. So it looks like we're done. So you're going to have 3, 1, 1, 3. All right. So let's see if that works out. And then now we have barium hydroxide and H3PO4. You notice the C here is in the reaction 1 of 3113. So we've gotten that one. So at least that's on the list. Now barium hydroxide and phosphoric acid is going to be a little bit more complicated, but we'll get through it. Let me move this. Barium hydroxide plus H3PO4 In the interest of time, I'm not putting in all the, the states, whether solid or liquid or aqueous or so forth. And that's going to be, and that's going to go, oh, boy, and that's going to give you, it's going to have to give you barium phosphate, which is anytime you have a +2 ion, or, a charge of 2 on one ion, a charge of 3 on the other, you really have a messy looking situation, but you just really need to get used to it. So it's going to be barium phosphates, 2 barium, so it's going to be, should be barium 3 PO4 2. The phosphate is 3 minus, barium is 2 plus, so 3 times 2 is 6, 2 times 3 is 6, so that looks like it's okay. And then you're going to have water. And of course, this barium phosphate is not going to be soluble. It will be solid. You see how they have that written. Oh, not there. Okay, as you see, this is a solid, and we're going to have to play around with this a little bit. So let's balance the hydrogens and oxygens first. So you have 3 hydrogens here and 2 here. So now you're in a little bit of a, you have 2 hydrogens on one side, you have an even number, so you would need 2 hydrogen ions to balance this, but you have 3 here that you have to account for. So when you have something like that, you end up cross multiplying them. So what you're going to end up doing is you're going to multiply the barium by 3. So you're going to have 3 barium hydroxide plus, and you multiply this by 2. And what's that going to give you? That's going to give you, well, you see, barium is balanced here. You got 3 bariums here, you got 3 bariums here, so that's good. And you've got 2 phosphates here and 2 phosphates here, so you're in good shape there. So it's going to be barium 3 PO4 2. Now we have to put something together for over here. So you have, how many you have? Well, you have 3. Well, you have 2 hydroxides on each barium hydroxide unit, and you've got 3 of those units in the equation. So that's 3 times 2 oxygens. So that's going to be 6 water molecules total. So count this up. Okay, we have we have 12 hydrogen atoms. So where do they come from? You've got 2 times 2 times 3. That's 6. Plus 2 times 3 makes 12. So that's okay. We have 3 bariums here, 3 bariums here. We have 2 phosphates here, 2 phosphates here. So it looks like we've got it. So we're looking at 3, 2, 1, 6. Okay, do they have that option? They have 3, 2, 1, 6. Look at that. So when you do this, you see they rate the reactants and products, balance the hydrogen and the acid with the hydroxide and the base, which we did, and then you have to balance, well, they did that, so balance the water with the hydrogen and balance the water, balance the H and S. Okay, you end up, you have to go through all this here. You've doing that a couple of steps. This is essentially what we did. So you end up with the 6 waters. You get the waters, the hydrogens, the hydrogen ions, the hydroxide ions in the waters in order, and then you take care of the salt, and then it's 3, 2, 1, 6. So that's pretty much what we did. Okay. Now titration. Titration is going to take a little calculation, but it's a laboratory procedure that you're going to use it to determine the molarity of usually an acid. You take an acid, you don't know its concentration, so you use a solution, a standard solution of a base such as sodium hydroxide to neutralize a measured amount, and it's going to give you you're going to be able to figure out the molarity from that, and we'll see how that works. They use phenolphthalein as an indicator to identify the end point. When you hit the end point, the phenolphthalein is going to turn red or pink or something. Depends on maybe how much you have in there. It's usually pink. You only want a couple drops. See, because that's an acid-base reaction too, and you don't want to have so much in there that it interferes with the results you're going to get from whatever you're titrating. This is what the setup looks like. You have a container, in this case a flask, containing a known amount, a known volume, milliliters, liters, of the acid solution, and there's a burette there that is graduated in milliliters, where you have you add this dropwise, you stir it, and you wait for the color change. Then you measure how much base you've added to get to the color change, and then you do your calculations. So the indicator is phenolphthalein. You see there, and you see this picture in the flask. You can see the liquid turning pink, and you stir this, and a couple of you're gonna have to do this a couple of times. You see the pink color, and then it disappears, and then a couple more drops, and then eventually the pink color it stays pink. See, like what we have here. So the moles of the base equals the moles of the acid in solution. The base meaning hydroxide, and the acid meaning essentially hydrogen ion, although whatever comes off as hydrogen ions. And the volume of the base, you measure the volume of the base the concentration of the base, because that's what you're titrating with. You know the volume of the acid solution, and you're going to know the volume of the base used. Then the molarity of the acid is used to calculate the neutralization equation for the reaction. Now, what do we go to next? Here's the way you do that. You take a look at, well, we're working in moles. Remember way back I said something about you always go through moles. So what you're trying to do when you essentially calculate the moles of base that you added, and you know that from the chemical equation, you know how many moles of acid you had, because when you reach the end point, you've added the same number of moles of base as you have of acid. So you're given 18.5 milliliters in this case of 0.225 molar sodium hydroxide and 0.0100 liters of hydrochloric acid solution. So that's going to be, let's see, that looks like, was it 10 milliliters? Well, they give you the liters, so we don't need to. Well, we're going to have to go from milliliters to liters, but in the case of the base, but here's what you're given. So then we move on. You do this where molarity is, well, there's the statement of the problem again, and you write the plan. You start with the milliliters of sodium hydroxide. You have to convert those to liters. Then you have to get to the moles of, you've got to get to the moles of sodium hydroxide. Moles of sodium hydroxide are going to be the same as the moles of hydrochloric acid. You divide by liters, you get the molarity of the solution. And here's the okay, here's what all they're doing. Let's do it with the whiteboard, just so you see the process worked. All right. Okay, so here I've put down the givens here. You have the 18.5 milliliters of 0.225 molar sodium hydroxide. So you notice we've got 3 significant figures there, 3 significant figures there, 3 significant figures here. And to find a concentration of hydrochloric acid, this brackets, I think I've said this before, but this is a convenient thing to use. If you have that, that means molar. That usually, in general, it means concentration, but really we're talking about molar, so that's the concentration. It's an easier way to write this. Okay, find the molarity of HCl. So, well, you have, if you look at the plan, you have to go from milliliters of NaOH to liters of NaOH. Then you go to moles of NaOH. And the moles of NaOH is going to equal, in this case, the moles of HCl. And then from the moles of HCl per, then you can get to the concentration there, because you've got liters, 0.01 liters, and then you'll have what you're looking for. So let's see how this works out. You have milliliters of sodium hydroxide. We got 18.5 milliliters NaOH. Times, we need a conversion factor. We need to get to liters. Okay, so I saw this in another textbook actually last night, where when you want to convert to something, your conversion factor is what's desired. Okay, the units that are desired units. Per given units. That's a nice way of looking at it. Okay, so you want liters here in this case. You want milliliters to liters. So let's we back up on this and get rid of this. Okay, times, we need liters per milliliters. And what's the conversion factor? We have 1 liter per 1,000 milliliters, right? You got 1,000 milliliters in a liter, so 1 liter times 1,000 milliliters. So there's your conversion. You're going to divide that by 1,000. And now you have liters of sodium hydroxide. And what's your concentration? You have 0.225 moles per liter, right? That's what that capital M stands for, moles per liter. Notice that now liters cancel. If you go through this where we are, you got milliliters cancel, liters cancel, liters cancel. You know what? I made a little bit of a mistake here. Okay, now we're okay. Okay, so now you have moles of sodium hydroxide. And we could do this. If you look at the chemical equation, I don't have the chemical equation up here, but it is over here, I believe. Yeah, you see the equation's here. So it's 1 mole of sodium hydroxide per mole of HCl is going to be the way the reaction works. So you have, now this is moles of sodium hydroxide right now. This is moles of NaOH, okay? And you have 1 mole of HCl per 1 mole of sodium hydroxide. And here's where it gets a little complicated, because you have to keep when you're working with these reactions, it's how many moles of one thing equate to a mole of another. So it's going to be the same number of moles, but this is the way you would do it. This is all mole. This is moles of sodium hydroxide up to here, and then you get this conversion factor. Now you have moles of hydrochloric acid, and that's going to give. So now you have moles of hydrochloric acid. So this is what we've gotten here is we've got rid of milliliters, liters, and now moles of sodium hydroxide. So now we have moles of hydrochloric acid, and well, what's the molarity? Moles per liter. How many moles do we have? We already have 1 over, just divide by liters. So we have 1 over 0.0100 liter, and that's going to give us our concentration. So let's run the numbers. Okay, you run the numbers, you go through all this, you're going to see you're going to have 18.5 divided by 1,000 times 0.225 divided by 0.01. Is remember, you've got moles here, and you've got moles per, you've got however many moles this is per 100th of a liter. So what you end up with when you do this, if you do the calculation on your calculator, is going to be 41625, and that's the concentration there. Now, we talked about significant figures. Well, there's 3 here, 3 here, 3 here. So everything's 3 significant figures, so we have to round to that. So this, here's your 3 are going to be 416, that's 3, and then after that you've got a 2, so that's going to be rounded to 0. So you're going to end up with 0.416 molar. All right, that's going to be your answer. And you see when we do the math, that's what we get. So that's the same thing that I just did. You just keep canceling units. You work towards, you started with milliliters of sodium hydroxide, and you convert that to liters. Then you convert that to moles of sodium hydroxide. Then you convert it to moles of hydrochloric acid, and that's going to be that many moles per that many liters that you have. That's the number you get. Okay, so that's the way you do these calculations. So what's the molarity of a hydrochloric acid solution, or an HCl solution, if 25.5 milliliters of 0.438 molar sodium hydroxide is required to neutralize 0.025 liters of HCl? All right. Well, let's do that again. Let's go through the whole process. We have, let me clear all this. Well, told it to clear. There we go. This is a long section, as you've noticed. Okay, we have 25 mil. We're given 25.5 milliliters of 0.438 molar sodium hydroxide, and you have 0.0250 we have 0.0250 liters of HCl. Same process here. Okay, so you have to do some conversions there, but you really only have 3 numbers to work with. So let's do this. You have 25.5 milliliters of, that's going to be times 1 liter per 1,000 milliliters times 0.438 moles per liter. Remember, that's what that capital M means, moles per liter. And this is moles of NaOH. There, it is NaOH, right? And that's going to be the moles of NaOH, and it's the same basic reaction. So you have 1 mole of HCl per 1 mole of NaOH. So now you've got moles of hydrochloric acid, and that's moles of hydrochloric acid in 0.025 liters. 0.025, yeah, it's 0.0250 liters And that should give you your molarity of HCl. So what do we have? Okay, so we have 25.5 milliliters divided by times 1/1,000, or divided by 1,000 liters per milliliter. And we multiply that by the molarity, 0.438. We're switching now. We've got, that's where we're at the moles of sodium hydroxide. It's 1 mole per 1 mole. The hydrochloric acid and sodium hydroxide, and then you get 0.438 there, and then you divide that by 0.0250, and you get here you get what? You get 0.44676, 0.44676, and that's molar, but we only have 3 significant figures. Right? There's 3 there, 3 there, 3 there. So 446, there's your 3rd significant figure. And the next decimal place is a 7, so you round that up. So you have 0.447 molar. Okay, that should be your answer. And you can, you're gonna have access to this video. Well, you're watching this video, so you can stop it and look at this if you want. You go through all that. These conversion factors, and they don't show you the rounding process, but it's 0.447. I'm going to show you one more trick here. If you really grasp what you're doing here, the concentrations and you understand that you've got to go, if you're looking for a concentration, molar concentration, you're in moles per liter. And if you recognize that, and sometimes you can actually do these calculations in your head, if you look at that equation up there, C1V1 is equal to C2V2, and it seems like there was some dilution problems that you had to do in the solutions section. The same thing works here. Okay, the C1 times V1, that's concentration times volume. So concentration in molar, volume in liters, so that's going to be moles, and that's going to equal the moles of your number 2. So if C1V1, if 1 is sodium hydroxide solution and 2 is the hydrochloric acid solution, you're going to have to do what you're going to need to do is you're going to have to, well, you're given 0.250 liters here, and you have 25.5 milliliters, so you have to turn that into liters, which you divide by 1,000, so it's going to be 0.0255 liters, and this is molar. And you do that, see, this is this equation here, and you're going to end up with 0.44676 molar. And then, of course, you round that to 0.447 molar. That's, you really have to understand this well in order to use that little trick, but that's really what you're doing. That whole sequence that I just showed you is, and the book, the slide show you too, is something like that. So if you feel confident doing that, it'll save you some time. But anyway, you do get the answer as expected. We talk about antacids here. Now we're done with the calculations. Antacids are basic substances. They are used to neutralize excess stomach acid and, relieve heartburn, something like that. They're often aluminum hydroxide, magnesium hydroxide mixtures, but they have carbonates, various carbonates. Well, it's pretty much hydroxides and carbonates that they're going to use. They're not very soluble in water, for good reason, because, well, hydroxides are very strong bases, so you don't want to take, like, sodium hydroxide would work as an antacid, but you don't want to ingest sodium hydroxide. It would be a bad thing. So you take aluminum hydroxide, magnesium hydroxide, they don't really dissolve in water all that well, so they're not going to damage the stomach or the intestinal tract. And here's some of the common ones. these are the basic compounds in antacid tablets. And you see there are a couple of, you have calcium carbonate and sodium bicarbonate or potassium bicarbonate in Alka-Seltzer. And they're just neutralizing excess stomach acid. So that's an acid-base reaction. If you ever have heartburn and you take an antacid, well, you know what's going on. These things like omeprazole, some of those, they work differently. They actually interrupt the production of stomach acid in some way. But that's what antacids do. Okay, well, this has been a long session here, but we're done. And we got one more section, and then we're going to be done with this chapter.